Today, our topic of discussion is decomposition, and we know that why we need decomposition. So, whenever we are talking about a particular relation R, and if this relation is, say, not in particular normal form, say it is not in 2NF, not in 3NF, or not in BCNF, then the only thing that we will do, we will decompose this table into two parts, two or three part. So this thing today we have to learn. That is, first we have to know what is this decomposition. So it is a process of breaking up or dividing a single relation into two or more sub-relations. It is called decomposition of a specific relation. Now we have two types of decomposition. One is lossless decomposition and another one is lossy decomposition. So here what we have to find out today, whenever we have certain decomposition for a certain relation, we have to check how to find out whether this decomposition is lossless or lossy. So this concept we have to learn. So now here the question is, what do you mean by this lossless decomposition? Lossless decomposition means, say for an example, I have a particular relation table R with three attributes, and if I decompose this relation into two parts, that is say R1 and R2, here this decomposition is said to be lossless if we join these two relation again, we will again get back to the original relation. This original relation will be found. So if this situation occurs, so this kind of thing is known as lossless decomposition. But how to find out whether a particular decomposition is lossless or lossy? So for that purpose, what we will do, we will follow some rule. If we follow those rules, then we will definitely find that whether a particular relation is lossless or lossy. So what are those rules? So we have to keep in mind. So here the condition number one is, so whenever we are dividing R into two decomposed part R1 and R2, then the condition number one is, if I take union of R1 and R2, then we should get back to the original relation. Means if we join this two relation, decomposed relation, we should reach to the original or initial relation. So this is the condition number one. And condition number two is, if we intersect this two decomposed relation, then it should not be phi. Means between this two decomposed relation, there should be one common attribute. If there is no common attribute, it is known as phi. So it is not acceptable. So this is your condition number 2. Now we have condition number 3. So what is that condition? If we take intersection of these two decomposed relation, we should get a super key of either relation R1 or relation R2. So this is the three condition that we have to memorize. But here the problem is, memorizing this three condition will be difficult if we don't understand this. But I will give you one example by which you will be able to understand what is the meaning of this three condition. But before that, I want to state you one thing. We have to check these conditions one after another. So if certain condition fails at any point of time, so we will stop here. We are not going to check the next condition. So we will here declare that it is a lossy decomposition. So here my point is, if condition number 1, 2 and 3 is satisfied, then only we can say it is a lossless decomposition. Otherwise we will say that it is a lossy decomposition. So now I will give you one example. Now consider one specific problem. Say one relation is given to you, and here we have some set of functional dependencies, that is A to B, B to C, C to D, and D to B. Also, it is given that this relation is decomposed into certain part, that is, say R1, R2, and R3. Now, here the point is why I am taking this example. So, we have to prove it is a lossless or lossy decomposition. So here try to understand this is a unique example, and this is a most important example that I am discussing today. So here try to understand we have three conditions to check whether a particular relation is lossless or lossy, but which is not mentioned anywhere. That thing I want to add. So see here how many decomposed versions are there. So in general, what happens? A particular relation will be decomposed into two parts in general. It is a very common example. However, mark this point and take a note here. Whenever a particular relation is decomposed into more than two parts, then what you have to do? Then you have to do one thing. You have to take the original relation and don't write it like this: R1, R2 and R3. So dividing this three part into one step, it is not possible. So what we have to do, we have to write the original relation, then we have to divide it into two part. Say in one part we have R dash with some attribute, and in another part say I have another two attributes, say B and D, and then further subdivide this portion into two, that is R1 which is AB and R2 which is B and C. So here remember this point, do not write directly this three division. So always whenever your original relation is divided into three part, create one intermediate portion and then try to reach to the decomposed version R1, R2, and then R3 will be reached from the first initial condition. So this thing you have to remember. So this is a very, very important thing. Now we have to prove that whatever decomposition we have performed, because it is given in the problem, and it is lossless or lossy. But here there is one question, from where I am getting this R dash. See, we know that this part will contain R1 and R2. So R1 and R2 is having A, B and C attributes. So that's why R dash is having three attribute A, B, C. So instead of writing R1 and R2 directly, we have to write this intermediate position which is containing all the attributes of R1 and R2. So it's a simple step. So this thing you have to remember. Then only we will go and check the rule of decomposition. Now let's start finding whether this relation is lossless or lossy. So now let's check. So what is your condition number one? So according to the condition number one, what we have to do, we have to pick up this two decomposed version. The first decomposed version R dash and R3, and then we have to check if I take union of these two, then whether I will be able to find out the original relation or not. So here my first decomposed table is ABC, and the second decomposed table is containing B and D attribute. So I will take union of this two decomposed table. So union means I will join this two table. So After joining this two table, I will get A to B attribute, means I will write B once, then C, and then D. So here basically first condition is satisfied. So after decomposition, whichever decomposed portion we are getting, if I join these two, then, then I will be able to reach the original relation R. So since this condition is satisfied, then I will check the condition number 2. So what is the condition number 2? Then again I have to take this two decomposed version, and then I have to take intersection of these two. Taking intersection of these two decomposed version means I have to check whether there exists any common attribute or not. Yes, we have common attribute as B. So from here I am getting B, means B is the output of the intersection of these two decomposed version. So here according to condition number 2, if I take intersection of these two decomposed version, it should not be phi. So here we are getting B, means it is not phi. It means common attribute exist. So again it is satisfying the condition number 2. So now I will move on to the condition number 3, which is very important. According to the condition number 3, what we have to do, again we have to take the intersection, means whichever intersection we have performed and whichever attribute we have got as a common attribute, I have to prove that this common attribute is a super key. But is a super key of whom? Is a super key of either R dash table or it is a super key of R3 table. This thing I have to prove. Now how to prove that B is a super key or not? So the only thing is I have to find out closure of B. So how to find out closure of B? So rule of reflexivity, from B I am getting B, and from B, B is in the LHS, in the functional dependency, I am getting C. So I am including C over here. From C, C is appearing in the LHS of the functional dependency, I am getting D. From D, again I am getting B. B is already there, I am not including it. But here, so closure of this B is B, C, D. Now you have to check B is a super key of whom? See, you have to check B, C, D attribute exist in which relation? See, B, C, D. No, it is not here. Again, B, D. No, it is not here. So what we can say that closure of B cannot determine attribute A of the original relation R. So it is not a super key of original relation R. First point you can conclude. But attribute B can determine all the attributes of relation R3. Means here is the trick you have to understand. From this attribute B, means closure of B, I will be able to reach two attributes of relation R3. It is clearly visible. So in this case, what is the conclusion? Try to understand. After finding closure, which attribute is absent? A attribute. A attribute of the original relation is absent. So it is not a super key of relation R. Now I will check, is it a super key of relation R dash? So it is again not finding A. A, it will not be able to find A. So it is not a super key of R dash also. So but it can find all the attribute, means B and D, from its closure. So I can say that closure of B is a super key of the decomposed relation R. So here my point is condition number 3 is also satisfied. That is, whichever common attribute I have got after the intersection, this attribute, if I find closure of this attribute, then if it finds any of the relations attribute completely, then it will become a super key. So it should be super key of this one, or it should be super key of this one. So in this case, B plus means closure of B is a super key of R3. So here we can say that condition number 3 is satisfying. So in this case, the entire relation is lossless decomposition. So this is the example that you have to consider. So now here it is a very important point. In any of the material, you will find this proving these two conditions. But my point is, first check in the interview or in the question paper, i- the given problem is decomposed into how many decomposition. If it is more than two, like this, then you have to create one intermediate section and then try to reach this one. And whichever intermediate section is created, then you try all the three conditions on this three cases, means on this two decomposed version, right? So then only you can say that the decomposition of R1, R2 and R3 are lossless, because there is no need to check, because this thing and this thing is satisfying all the three cases. It means this two will also satisfy all the three cases. So this is one of the most significant example that you have to remember all the time. However, we have many other discussion too. So we have other example too that we have to check. Say we have a relation like this: R, A, B, C. Say it is decomposed into two portion: R, AB, R1 AB and R2 BC. And the functional dependency exists A to B and A to C. So here my question is, this decomposition is lossless or lossy? So what you will check? The condition number 1 is, you have to check union of these two. The rule is, after joining these two relation, I should get the original relation. Now if I join these two, I will be able to get R, A, B and C. See here, if I join this two table, I am getting the original table ABC. So here in this case, what we can say, it is a lossless decomposition. Now, can we check the second condition? You can check R1 intersection R2. Means how many common attributes are there? Means is there exist any common attribute or not? Yes, we have the common attribute, that is B. The second condition is also satisfying. Now you can also check the third condition, that is B is a super key of any of the relation or not. So you have to find out the closure of B. So here the closure of B means from B I am getting B only. So this B means which attribute? None of the R1 and R2 is reachable. So in this case, what is your conclusion? It is a lossy relation. So here my point is, you have to check all the three cases one by one. So do not try to conclude after visualizing only one condition. So this is the very important thing you have to remember. So now let's check one final example. Now we have understood now what is the problem. So here the relation is given like this. This is a very common example which is asked in the interview. That is, this is the relation and the functional dependency which is given as A to B and C to D. And the decomposed relations are also given: AB, R1 AB and R2 CD. So here again the question is, it is a lossless or lossy. So what we will do? First, we will check our condition number 1. That is, we will take union of these two decomposed version. So after taking union means after joining this two table, I have to get the first one means the initial table. So here after joining this two table, what I am getting A, B and C, D. So here my point is clearly condition number 1 satisfies, but do not conclude over here. That is okay, it is condition number 1 is satisfying, so it is a lossless decomposition. No. Then go for the condition number 2. So what is the condition? The condition is now we have to check intersection of this two relation. Intersection means just we have to find whether there exists any common attribute or not. See, clearly between R1 and R2 there is no common attribute. So it is phi. So it is violating the condition number 2. So it is not satisfying the condition number 2. Means if there exists no common attribute, then condition 2 fails. So at this point of time, it is lossy. Now my point is once you have got the proof that this decomposition is lossy, no need to go further to check condition number 3. So this is my point. So at this point of time, you can conclude that this decomposition is lossy. So what is my final conclusion? If your conditions are satisfying, so whenever your first condition is satisfying, go for 2. Second condition is satisfying, then go for 3. So for satisfying conditions, you have to move forward. But if some condition fails at certain point of time, stop here and declare it is lossy decomposition. So this is the thing you have to remember. So whenever I have one relation like this, and we have functional dependencies like this, now in this case, say we have two decomposed version. Now in this case, what kind of decomposition it is? Lossless or lossy? So first what we will do, what we have to check? Condition number 1, that is union of this two decomposed version. So if I take union of this two, check what I am getting: xy, 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 z, z1. So I'm getting back, right? I'm getting back the initial relation. Hmm. So in this case, we will not stop here, right? We will move on to the second condition. So I will take intersection. So if I take intersection of these two decomposed relation, so what I will get? Common attribute. So which attributes are common? X and Y. X and Y, common attribute I am getting. We have XY as a common attribute. Now we cannot stop here. So we have to check closure of XY is a super key of either this relation or this relation. So from XY I am getting XY, and from X I am getting Y. It is there. It is not Y1. And from Y I am not getting anything. So from XY I am not getting complete attribute of any one of the relation, right? Neither this three nor this three. So at this point of time, we fail to prove condition number 3. So it is lossy decomposition. So we may fail at any point of time. So this is your lossy decomposition. So is this condition clear?